Now, for our third example, we compute this infinite integral. Okay, the integrand is exponential of minus x squared, but the antiderivative of this function of our integrand is not an elementary function. So the method we learned in the study of single variable calculus could not apply to compute this integral. Okay, what should we do? So we raise the dimension, transform the one-dimensional problem into a two-dimensional problem, and then this can be solved. So let IR be the integral of our function from minus R to R. Okay, then we have the following relation: BR contained in this rectangle, and then contained in a larger ball, larger disk. So we consider this picture. The red, maybe I made something wrong. Anyway, this sorry, BR obviously is contained in this rectangle. Okay, this is quite obvious because the length of the edge of this rectangle is 2r, precisely the diameter of BR, and the center is the origin. Both the center of the disk BR and the rectangle is the origin. Therefore, this is easy to see. Okay, and moreover, this rectangle which range 2r is contained in the disk which radius square root of 2r. Okay, this can be seen from this picture. This blue rectangle is our rectangle minus r plus cross minus r, and the red circle bound a disk which contained the rectangle we considered. So what is the radius of this red circle? Because this length is 2r, therefore the diameter of this rectangle is square root of r. So 2 square root of r. Therefore, the radius of this circle is square root of 2 multiply r. Therefore, this is b square root of 2r. Okay, this is easily checked. I'm sorry, I draw a long picture. I should bound a smaller circle inside this rectangle. But I made something wrong. Okay. Anyway, we have this inclusion, and our integrand is a non-negative function. Therefore, a non-negative function, the integral of a non-negative function will be larger if you integral over a larger domain. So the integral over the smallest domain BR will not greater than the integral over this rectangle. And also this integral, since this is an integral over a rectangle, we can apply the Fubini theorem to write this by iterated integral. First integrated with respect to y and then x. Now this integrand is e minus x squared multiplied by e minus y squared, and when you integrating with respect to y, the e minus x squared does not depend to y, therefore it is a constant. It can be moved outside of the integral over y. Therefore, this can be written by this. So both these two integrals are IR. Okay, they are the same, except that you use different letters to denote integral variable. Therefore, this is IR squared. But this integral, this double integral, is also less than or equal to the integral over the larger disk, because this disk contained the rectangle. Okay, so we have this estimate. Now we compute this integral. We compute this integral. We will compute this integral and consider when r goes to infinity, what happened. We will prove that when r goes to infinity, both sides of this inequality converge to the same number. Therefore, ir square also converge to that number, to the square root of that number. Then this gives us the result we want. Okay. So as r goes to positive infinity, this integral we use the polar coordinate x equal to r cosine theta, y equal to r sine theta. Okay, so this integral can be written as an integral over r from 0 to r and theta from 0 to 2 pi. So since that integral with respect to r theta is over a rectangle, it can be apply the Fubini theorem. First, the integral with respect to r and then theta. So for the integrand, this becomes exponential of minus r square. Where is this r come from? This r is the Jacobian determinant. You change the variable of an integral, you need to add a Jacobian integrand in the you need to add the Jacobian determinant to the integrand. Okay, so the new integrand is the replacement, substituting of the original integrand multiplied the Jacobian determinant. Okay, this is you should not forget this r. Now the inner integral is easy to compute because this r you can let r square to be t, then r dr is half of dt. So this is exponential of minus t dt. So the antiderivative of exponential of minus t can be computed. Therefore, this inner integral can be computed using the antiderivative and also using the fundamental theorem of calculus. It turns out that the integral inside is this number. Then this number does not depend on theta. So this can be the value of this integral can be considered as a constant. Therefore, the integral of that constant over 0 to 2 pi is precisely 2 pi multiply this constant. Then as r goes to infinity, this goes to pi. Why? Because this goes to 0. Because the exponential of minus r square goes to 0. Okay, so this goes to pi. And similarly, you can see that when r goes to infinity, the right hand side of this inequality also goes to pi. Therefore, by the well-known result, we see that ir square goes to pi. So ir goes to square root of pi. So the integral we want to compute is the limit of ir. Okay, what's our ir? Our ir is this number. So when r goes to infinity, this ir converges to the quantity we want to compute. Okay, so our I is the limit of ir, which is square root of pi. Now we go to next example. So this example we will consider the cylindrical coordinates. So let omega be this domain in R3 in R theta z space. The coordinates are denoted by r, theta, and z. Here r is positive, theta is from the open interval 0 to pi, and z is free in the real numbers. Okay, and the corresponding d is the xyz space, three-dimensional xyz space, removing the half plane. This plane x is non-negative, y is 0, and z is free. So omega and d are open sets in r theta z space and xyz space respectively. Okay, why d is open? Because R3 is an open set, and this is a closed set in R3. An open set removing a closed set is open. Okay. Now we define the map phi over the closure of omega. So what's the closure of omega? The closure of omega is a cylinder, not cylinder, a column. Because are unbounded. Okay. Anyway, this map is defined in this way. X, Y, Z, the phi maps R theta Z to X, Y, Z in this way. Here X is R cosine theta, Y is R sine theta, and Z is Z. Okay. So this map, as you can check, this map obviously is differentiable. It is C1. And also on the closure of omega, it is not 1 to 1, but in omega it is 1 to 1. Actually, it is a diffeomorphism from omega to D. I missed something here. I should say phi is C1, and it is a C1 diffeomorphism from omega to D. I forgot to type something. And the Jacobian determinant of this map is the Jacobian determinant of the Jacobian matrix. So for this map, the Jacobian matrix is here. The first column is the partial derivative with respect to R for x, y, z. The second column is the partial derivative of x, y, z with respect to theta, and the third column with respect to z. And by a simple computation, you will see that this Jacobian matrix is given here, and the determinant is also R, just like the polar coordinate in 2 dimensions. So this is cylindrical coordinates. It's very useful when the integral you want to compute involving functions of x squared plus y squared, because for this x squared plus y squared is r squared. Okay. Now we consider this example. I is a triple integral. The integrand is x squared plus y squared, and then the integral domain D. What's the D? D is bounded by 2 surfaces. One is z equal to x squared plus y squared, and the other is z equal to h. So z equal to h is a plane parallel to the xy plane, and z equal to the x squared plus y squared is the parabola. Okay, so the picture is here. Here, yes. Oh, I forgot to add the picture of this domain. Okay. Okay, this is the domain. Here the curve is the parabola, and the horizontal z equal to h is the plane. So our domain is of this form. Okay. Now, so our domain denoted by D. So we use the cylindrical coordinates. The pre-image of our D under our cylindrical coordinate is given by the r theta z space omega here. Here z is from r squared to h. R is from 0 to square root of h, and theta is 0 to 2 pi. How to see this? Go back to the picture. So theta is the angle of the point with respect to the xz plane. Therefore, it is 0 to 2 pi, just like the polar coordinate. And for z is the lower boundary. The lower boundary is z equal to x squared plus y squared. This is precisely r squared. And the upper boundary of this domain is z equal to h. So the range of z is r squared to h. And for the r, how to determine this r? You project this domain into the xy plane. You will get a disk whose radius is h. Why is h? because z is h, the boundary here, the intersection of this parabola which the plane cutting the parabola to get our domain here, the boundary is z equal to h and z equal to x squared plus y squared. Then the boundary circle is precisely x squared plus y squared equal to h. Then you projecting this into the xy plane, you will get a circle of radius square root of h. This is the range of our r, because x squared plus y squared is r squared. Okay, so this determined the geometrical consideration determined the range of r, theta, and z in the corresponding cylindrical coordinate space omega. Okay, and so our integral is over d of this function. So using the change of variable formulas, we can rewrite this integral into a new integral over the new domain, the omega. Here the integrand is x squared plus y squared. This is r squared. Okay, and the Jacobian determinant is r for the cylindrical coordinates. So this integral becomes this integral over omega. But omega is not a rectangle. For omega, the range of r and theta are intervals. Okay, but the range of z is also an interval, but the endpoint of the integral depends on r. So you cannot let z be the last integral. You need to put z in the inside. Okay, so it is better to write this integral. First, the integral integrated with respect to z, and then r or theta. Okay, so this integral over this omega can be writing in this integral, iterated integral. Okay, for z from r squared to h, and then for r from 0 to square root of h, and for theta 0 to 2 pi. Now the inner integral is very easy to compute. That is r squared h minus r squared. And the outer integral, because what inside these two integral does not depend on theta. Therefore, for the outer integral, this can be considered as a constant and move outside. And then this outer integral, which with respect to theta, becomes the constant function 1, integrated constant function 1 over 0 to 2 pi. This gives us 2 pi here. And then we compute this integral with respect to r. It is very easy, right? So the result is 1 over 6 pi h cubed.